Looks like it's trying to work. There it goes. Once it gets to that part, you could just close out the window and it works just fine. Okay, looks like class can officially start. Hey, we made it just within the minute practically. Welcome back, everyone. It's now week 6, and we're at a pretty exciting part of the course. We're now turning over from learning about limits to actually applying them to something more useful than we really saw in chapter 2. In section 3.1, we define the derivative of f at a to be this limit. And then section 3.2 is just another look at the derivative. If you think back to what you've done in an algebra class, the moment you've discovered a new function, whether it's a linear function, a polynomial, or exponential, logarithmic, and so on, the very next thing you do is you want to plot those functions and get some geometric understanding of what they look like. And that's what section 3.2 is all about. So I think it's kind of a nice approach. We're taking our time when we're defining the derivative by going in stages. 3.1, mostly about cranking this out and getting a number, doing some tangent lines like we did in last class. And 3.2, we're just going to look at more intuition about the derivative, considering graphs, and calculating a couple more of these for extra practice. And note that formula is essentially the same, whether you're doing a tangent line equation, the derivative of f at a, or the derivative of f at x, it's always this same kind of limit. Well, that's where we're at so far, folks, and that's where we're going. Any questions or comments to start us out? Okay, well, let's get going. So we got pretty far to section 3.1, but instead of jumping to that last problem, it was a long weekend, so let's refresh just a little bit. This is really what we're dealing with. If we want a tangent line to a curve y equals f of x, that's this one in black, right at a point, af at a, that's this point here, essentially what we're requesting is the slope of the curve in black at exactly 1 point. In order to do that, what we did was we took a secant line. Let me zoom in just a bit. The secant line got us 2 points, so we can calculate the slope of this line in green, but the slope of the line in green is never the slope here in yellow, the blue line that we're really going for. So we still formed this equation in the slope, here it is right here. We simplified it, and then we observed, if we take the limit as h, that's just the increment that moved the point A to a new location. As h gets smaller and smaller, this dot moves down the curve, slowly overlapping with the one in black, and that means the secant line is getting closer and closer to the actual tangent line, the one we're interested in. So all we needed to do was put a limit in front of it, and now we're calculating the slope of the line right here, the tangent line, which is the instantaneous rate of change of this curve right at that point. We'll look at an application in this section too, just to get a feel for what do we even mean about instantaneous rate of change, and why are we so suddenly interested in slopes? But that was our recap from last week. Any questions at all, folks, with this drawing here or the definition? Okay, definitely riveting stuff. Then after we took a look at this definition, we did 2 tangent line computations. They go right back to this limit here, and it's essentially what we were doing in sections 2.4, 2.5, calculating these limits, doing them algebraically with limit laws. But by the way, notice we don't directly cite the limit laws. It's just a long list of things that we're allowed to take for granted. And this is how the limits were generally going to be going in chapter 3. No direct citation of a limit law whatsoever. Then we did it again with kind of a trickier function. This one involved a conjugate. And finally, this is where we landed. This problem is a little bit different, but now we finally define what we mean by the derivative. When we say derivative, we put an extra symbol right here called f prime. Might as well put that on the notes. This is read as f prime. The prime is referring to this symbol right here by the red dot. It's not an exponent, so you always want to give it a bit of an angle, like 60 degrees from the horizontal, because if you say f power 1, that might have a different meaning entirely. We really want to say f prime by going that way. But whatever we call it, whether we call it the slope of the tangent line or just the derivative of f at a, It's always the same exact limit. So that's the same limit we had at the very top of the notes. So we'll practice taking a look at more computations with this and do an applied problem at the very end. Any questions whatsoever, folks, with the notation? Okay, so in the homework for the WebAssign, you'll be calculating f primes like this one. It says f is defined as just an ordinary function of x right here. And we want to know what is the derivative of f at a, so f prime at a. It's a little bit different since we don't know the a value. So we're doing this for any a that would be in the domain of f, so we can't put in -3, but a could be 2, 1, 0, all sorts of values. We want to know what is the value of the derivative for all a. So here's how it goes. We begin by pretty much just writing this out. F prime at a is going to be the limit as h goes to 0 of f at a plus h minus f of a, all divided by h. Then that's our f of x function, so we just need to plug things in and crank out the limit. It's a little bit trickier this time because we're dealing with fractions, so we'll go very carefully with this one and make sure we have it all in pat. So first thing to take a look at, f at a plus h is just putting a plus h here and here, highlighted in yellow for the function. So this turns into the limit as h goes to 0. Well, because we have a fraction, it might be a good idea to organize this a little bit better. You can take the h that's in the denominator and convert this into 1 over h multiplying through the numerator. So it's just a little neat trick to kind of organize the mess we're about to put out here when we put in f at a plus h. So division by h, in other words, is equivalent to multiplying by the reciprocal of h. And now this turns into 2a plus h plus 1 divided by a plus h plus 3. So all I've done is for f at a plus h, through the a plus h's there and there, and that's the result here. Next step, we just put in minus f of a, so here's the minus sign coming in. F at a is not so bad, that's just changing x to a literally, so we'll have 2a plus 1 division by a plus 3. So that's our limit to take. And again, the only reason 1 over h is out in front is just to avoid the complex fraction where the numerator is now that. We might as well visualize it like this to organize it better. But that's really just a stylistic choice. If you prefer, you can keep your h down there. Now to do this limit, these are kind of nasty. We did something along these lines at the end of the section 2.4 notes. But what it boils down to is we need a least common denominator. So let's scroll down a bit and write that out for the next step. We have limit as h gets smaller and smaller of 1 over h multiplying. Strategy here is you want two pretty big fraction bars. So I'll go this minus this. That might be slightly dramatic, but we'll just see how my penmanship goes. And to organize the results better, let's just distribute the 2 through. So we have a 2a plus 2h plus 1, a plus h plus 3 down below, and then 2a plus 1, a plus 3. I'll put parentheses around anything that had more than one term. I guess that's everything here, just to be careful with our algebra. And then the name of the game is just to complete the denominators. We want to make them identical. What we do then is, this is the larger denominator. It's missing a factor of a plus 3, so we just plug it in. Above and below. Then likewise, we move over to this denominator. It has the a plus 3 on the left, but it's missing a plus h plus 3, that first factor. So we throw it in above and below. A plus h plus 3. Now that the denominators are equivalent, we can subtract across the numerators. So a lot of writing to start. It gets a little bit messy, but if we're really careful with the distributions, there's a ton of cancellations. I would say this is the critical step right to that stage so far. Any questions at all, folks, at the moment? Okay, well, let's Start distributing through the numerators and see what we get. So this is now equal to, oh, let me change the color here. The limit as h goes to 0 of 1 over h times, now we can just put in one big fraction bar. The least common denominator we'll just write in once, a plus h plus 3 times a plus 3. And just to organize the note, I'll take notes. I'll just take one extra step and write in the numerator and distribute on the next step. So it's going to be this 2a plus 2h plus 1 is now multiplying a plus 3 minus the result of those two multiplying 2a plus 1, a plus h plus 3. And on the next step, we begin the distributions of this term, these two factors rather, and these two factors. So here it goes. It's limit as h goes to 0. Because we're multiplying fractions, we can now just write one fraction bar. Thank goodness we don't need the least common denominator. We'll just multiply denominators through. H times a plus h plus 3 times a plus 3. So now we're in business. We just need to FOIL through the numerator. We want to be really careful when we do that, so I'm going to put in little marks here so I don't miss anything. I think it's easier to distribute the binomial into the trinomial, so I'm going to start by taking a and multiply it through everything in that group. So we'll get 2a squared plus 2ah plus a. Next step, take the positive 3 right here and distribute it into the group on the left. That's going to give us plus 6a plus 6h plus 3. Okay, done with that distribution. All we have to do is now the rest over here. The negative sign is a bit of a nuisance. There's some tricks you could take to make it less of a bother. You can make this a plus and distribute the negative into one of the groups. But I'll just do it directly with what we see here. Might take an extra step. My first step is just to make the fraction bar longer. Then I'll carry in this negative sign. It has to distribute into the full result of FOILing these two. So I'll do the distribution of the negative sign on the next step. So just like before, go slowly and methodical to make sure you don't miss a single term. That's the hardest thing about this, organizing everything. But first it's 2a times the a, so 2a squared. Then it's 2ah. Then it's 6a. Then move over our focus to, this was not so bad. Positive ones distributed into the group. That just gives us plus a plus h plus 3 after multiplying through. Then close a parenthesis and one additional step just to distribute that negative sign inside. Any questions so far, folks, with the numbers? Okay, I think we're just about there. On the next step, it gets even worse to look at, but then we get a whole lot of cancellations. We have limit as h goes to 0. There's another long fraction bar. And I'm copying all the way to this step, or that term, 2a squared plus 2ah plus a plus 6a plus 6h plus 3. Really, the biggest danger for me is that there's just so much stuff that I think of the red dot as my finger moving across as I copy it in, just to make sure I didn't miss anything. Then on this stage, we're multiplying by -1, so it'll be negative 2a squared minus 2ah minus 6a minus a minus h minus 3, all of which is divided by h times a plus h plus 3 times a plus 3. Finally, after all that methodical work, we should have some cancellations. The one thing you've noticed is we can't calculate this limit until that h by the red dot is just eliminated. And the only way that h can divide out is if terms like this one that don't have a factor of h are canceled. So there's got to be an opposite of 2a squared somewhere, or else we made a mistake. Here it is over here, so we're on the right track. This one may or may not cancel, but the positive a here is required to cancel. But we're in luck, 2ah has opposite negative 2AH. Positive A has negative A pairing up, canceling it. Positive 6A, negative 6A cancel. And let's see, positive 3, negative 3 cancel. But there are two like terms that have not canceled. That's positive 6H minus H. So let's scroll down just a little bit more. The work is now, we have a limit as H goes to 0 of 5H. After combining those like terms circled, divide by H times A plus H plus 3 times A plus 3. Once we cancel those H's, there we go, done. We can now use direct substitution. As H goes to 0, we have a continuous rational function in the variable H. This part right here just goes to 0. So in fact, we don't write the limit statement any longer. We're directly substituting 0 there to get 5 over A plus 0 plus 3. Let me fix that 3 real quick. Times A plus 3. So following the yellow highlighting, that's the direct substitution there. This simplifies a little bit further. The denominator is just A plus 3 squared. So the result is 5 divided by A plus 3 to the power of 2. I would say that's the best way to format the answer. It's a little bit simplified in its factored form, more so than if you were to expand it. In fact, you might have noticed that in this entire semester, for dealing with limits, I have never expanded out the denominator. It's always convenient to leave it like this, fully factored. But if we follow our long chain of equalities, starting from here, all the way through, by the transitivity of equality, we have that the derivative of f at a is that quantity there. But just for the sake of summarizing a little bit better, let me put it down here. Let's say, therefore, the 3 triangles. This is a lot of work, so it's appropriate, it looks like. The derivative of f at a is equal to 5 divided by a plus 3 squared. Well, we did it, folks. That's the conclusion of this problem right here. We calculated another derivative. This one didn't want a tangent line, so we just stopped right at this stage. Any questions at all with this full process? See if I can zoom out there. Okay, well, this was a pretty hard computation. In the WebAssign homework, there's a lot more reasonable problems to get through, but I felt like this was a good one to bring to class just because there is a fraction in WebAssign, and that will support that next question. This is a tricky kind of process to get through, so we'll try it again in the next part, example 3, part B. But before going there, let's add just a little bit of description on what in the world did we calculate. That quantity depends on A. So imagine you picked an A. Maybe it's something like -2. You'd put -2 here, square it, and you just get 5. So what does the 5 have to say about anything? Well, that's going to be the slope at the value where x is 2 of the tangent line. So essentially, we found a formula that gives us a slope at any value A, so long as A is not -3. So to paraphrase that, we can say this equals the slope of the tangent line. Oh, before that, we got a chat. Thanks for the question. Dennis says, is the prime term describing only the derivative or its tangent? Oh, that's a great question. That's just describing the derivative itself, not the tangent line. So think of that prime symbol as a way to say slope, essentially. So it's just the slope of the tangent line at the point a comma f of a to the graph of, this is a longer sentence than I anticipated, to the graph of y equals, and I forgot the original function, it was 2x plus 1 divided by x plus 3. So this is what we're going to expand on a little bit more in the next section, 3.2, calculating a derivative like this, where the emphasis is a formula now, essentially, that gives you a slope at any value A that you pick. Well, other questions or comments at the moment? Thanks for the question there, Dana. Okay, well, let's try this out one more time. So same kind of process. We have a square root function this time. So if you're thinking conjugates, good on you. That's the algebraic trick for this one. And just like before, we're calculating f prime at a. So we just want the derivative essentially. Excuse me, got a hair in my eye. So the strategy for this is, I would encourage you to always, every time you see a problem like this, excuse me, first thing, just write down the definition of the derivative. It goes f prime of x. Oh, and kind of made a mistake there. There's nothing wrong with going f prime of x. If you did that in this section in the quiz that's coming due, that's assigned this week, I would give full credit to that. But the best thing to do is if they say f prime at a, let's put an a there just to avoid the confusion. In section 3.2, we do f prime at x. So copying what they want, f prime at a is the limit as h goes to 0 of f at a plus h minus f of a, all of which is divided by h. This one deserves a little bit of color coding, so let's put blue here, green here. When we plug in the limits, this turns into, or excuse me, the function values, the f of a plus h, for example, it turns into the limit as h goes to 0 of, first in blue, a plus h just goes right here for x. So it's square root a plus h minus a. Then minus to minus. This one is always never too major. We're just putting a for x, so it's going to be square root a minus 8. And so like a lot of problems, it turns into a mess at first. This is already a lot to deal with in a limit, but we have tricks and strategies that we can borrow now from chapter 2. We need a conjugate, and I didn't think this through. I don't have enough space here, so let me just write it again on a new line. So take the limit as h goes to 0. It's root a plus h minus 8 minus the root of a minus 8 divided by h. Now here we're multiplying by the conjugate. So all we do is copy in the numerator, but flip the sign right here in the middle that separates the roots. So now it's root a plus h minus 8 plus root a minus 8. Same thing in the denominator. Because this is now going to involve some expanding, I like to usually put parentheses around these, you might have noticed, just to help visualize what it should do algebraically next. And now we take the tedious step of multiplying through the numerator. It's not as tedious as it seems because there is a guaranteed cancellation on the middle terms. So if you take a shortcut, a lot less writing. I'll show it in full one more time in the notes just to show how this always goes. So following the arrows, multiply here to here, and it's a root times a root with the same thing in the inside. The radicand is the same. So you just pick up that radicand, a plus h minus 8. Then this multiplies from here all the way over here. Sorry, was there a question first? I thought I heard a whisper almost in Zoom. Okay, so next we'll take that first term, multiply it by that term, and that's a giant mess. This will just turn into plus root a plus h minus 8 times root a minus 8. And then we do it all over again. Now we multiply here to here. There's a leading sign negative, so it goes minus root a minus 8, root a plus h minus 8. And finally, when we multiply here to here, it's a root times the same root. We do have a negative sign, so this is probably the biggest danger right here. Oh, question first. Let me check the chat. Dan says, wait, so the derivative always has a formula, limit h goes to 0, f at a plus h minus f of a divide by h. Yes, absolutely. There's really two formulas, but the one that you cited is the one that gets emphasized the most since it's a general all-purpose formula. And that's always the definition of the derivative. Does that make sense with that formula there? Awesome. So last multiplication, we have to take that root with a negative sign out front, multiply by that root. And the reason this is a dangerous multiplication is we have to put in an extra parenthesis and go, don't know what that is, a minus 8 in this way. So that negative sign actually has to distribute through those two terms there. Then the denominator, we just write out in a factored form, h times root, a plus h minus 8 plus root a minus 8. So just like in the last problem, we expect a lot of cancellations, but we did mention that there is a guarantee. The guarantee is those terms and those terms absolutely cancel. They have the opposite sign. The only difference is the order. Sorry, question again, Kaylee?
So what was it when we woke up? 19.
Sounds like an open mic. Let me mute that. So with those two canceled, if that's a guarantee, you don't have to write that in on the next step. This is more just to show the process in the notes. The bigger danger is really that negative sign. So now let's do a distribution next. We have the limit as h goes to 0 of just a smaller fraction bar this time, a plus h minus 8. Over here, distribute to get minus a plus 8, all of which is divided by h times root a plus h minus 8 plus root a minus 8. So nearly there. Looking at the numerator, everything that does not have a factor of h, like that a, namely, must cancel. So good news, we have a and negative a. We have negative 8, positive 8 canceling. That means we can do one better. It's just h divided by h. There's no other terms, so this can cancel here to here. That means there's just a glorified 1 left over in the numerator. So even better, the whole reason we couldn't do this limit at the very first step or with the function plugged in is because we couldn't directly substitute in 0 for h. It's outside of the domain. But with that h canceled, just like in the other problems, direct substitution is on the table. So that term there just goes to 0. So we have finally limit as h goes to 0 of 1 divided by root a plus 0 plus minus 8 plus root a minus 8. And I did make a weird mistake on this one. This is a weird thing to put in. When you directly substitute in 0 to a spot right here, the best thing is to not write the limit statement any longer. We're done writing out the limit once we get to this stage. Let me see if I can fix that. It just looks weird now floating out on its own.
Can you explain one more time why you couldn't substitute the 0 in for the other h's?
For, say, on this step here by the red dot,
Yeah.
it's all because if we put 0 here, we would be dividing by 0. We'd have 0 over something else, and that would have been undefined at that stage.
Gotcha. Okay, thank you.
Yep, absolutely. And it's really unfortunate because if we could just directly substitute, we'd be all good. But this problem you see right here about that question is pretty much directly inherited from right up here when we're trying to take the limit, or excuse me, trying to calculate the slope based off 1 point. If we didn't do the a plus h, there'd be just 1 point in that denominator, which would have got us a 0 down below, or that would have been 0. So that's always the weird drama we have to deal with on a derivative using the definition, maneuvering through there. Other questions so far? Okay, so here I have a weird error with the limit. Once you take and directly substitute in 0 there, you don't write the limit statement any longer. So now I'm just recopying the numerator and denominator. Oh, and let's use actual pen to make it look official. It's now root a plus 0 minus 8 plus root a minus 8. So here's the 0 from direct substitution. That means our denominator is just root a minus 8 twice. Combined like terms, we get 1 over 2 root a minus 8. So finally, that's the derivative. For any value of a in the domain of this function, this will give you the slope of the tangent line. Well, any questions at all with that computation, folks? Okay, a great way to think about this is in a really strong way, just section 2.4 once again, along with information about 2.5. Really the only part that's new is this right here. The fact that our actual limit that we're calculating down below came from a specific formula. So think of section 3.1 as just doing more limits, but an extra formula to tell you which limit to calculate. Dennis says, does the slope work for any part of the function? Well, there's a part where it wouldn't work because the domain of this function goes from 8 to infinity. So that's the domain of the parent function. But when we went to go and calculate the derivative, notice the domain is a little bit smaller. This has domain 8 to positive infinity. Dennis says, so if you have an original function and are looking for the instant rate of change, you could use this for any domain on the original function, almost except for that 1/8. When you go to compute the derivative like we did, sometimes your domain gets just a little bit smaller. So you would have to put in, say, anything larger than 8. Say, put in 9, for example, and this would tell us the slope of that thing is exactly 1/2. Does that make sense so far with those questions? Awesome. That's awesome to hear. You bet. And let's just go along with that. Let's actually plot this and see how it's going. So here's our original function, f of x equals square root x minus 8. So domain starts over here, right at 8, only because we're avoiding complex value numbers. So here's our graph. And now we said if you plug in 9 in that formula, you would get 1 over 2 square root, just to emphasize 9 minus 8, but that's just a 1. You get a slope of 1/2. That means right over here at 9, there it is, we have a positive slope at exactly 1/2. And if I could get that dot on there, there it goes. That looks pretty believable to me, that would have a slope 1/2 for the tangent line. Doug says, I hope it will after copious amounts of studying. Awesome. Yeah, absolutely. Other questions so far, folks? Okay, so this is calculating derivatives, and we'll take a second look at all this stuff in the next section. But before we get too far, let's try one applied problem. So this is just, again, a rehash of the same definitions we've seen before. Limit as h goes to 0, f at a plus h minus f of a divided by h. This time the theorem is just giving us more information about the geometry of what this is calculating. We know it's a slope, but we can also call it the instantaneous rate of change of our given function with respect to x at a value a. So think of that as, again, some kind of slope. The problem we're going to be looking in is going to be velocities. Think miles per hour. This one is going to be meters per second. So on example 4, it says, we're going to have to trust the physicists on this one. If a rock is thrown upwards on the planet Mars with an initial velocity, so the moment it leaves your hand, it's going up at 10 meters a second, then after t seconds, the position of it is, let me reread that sentence, that didn't look grammatical. If a rock is thrown upwards on the planet Mars with a velocity of 10 meters per second, that's what I missed. Its height after t seconds is given by the position function s. So position function is something coming from physics. Sometimes this is referred to as displacement, and the symbol s is used to represent it. There's a kind of a short or drawback of using a variable s. Our formulas use function notation, so it's good to name the function. So sometimes, even if you're calling a position function s, we call it f of t on this, and this is the form that's going to take, 10t minus 1.86 t squared. We want to find the velocity of the rock after 1 second. So just for some notation to start us out, s is referred to as the position function, or just position for short. V is going to be the velocity. Think almost like if you're driving your car, if you're looking down at your speedometer, you're looking at a velocity. So velocity here is going to have either a positive or negative sign. Positive sign would mean the object's going up. Negative sign would mean the object's going down. And just to complete the notes, in later sections in chapter 3, we'll also look at this function, a, which would be acceleration. So this problem asked us, find the velocity, so we're thinking this function here, after 1 second. But that's just asking us to calculate the instantaneous rate of change, the speed at the exact moment, 1 second the rock left your hand. All this comes down as v, just to say we're doing velocity. 1 second, we'll throw a 1 inside there. But to calculate that, that's a rate of change of this function right here, the position function. So this turns into the limit as h goes to 0, f at 1 plus h minus f of 1, all of which is divided by h. So this time on this problem, we're just plugging 1 directly because they said 1 second. If they said any second on this kind of problem, we didn't ask any of that in the homework, but if it did, we would put in v of a, and over here it would have been f of a minus f of a, just like in the prior problems. But in this particular problem, we're more interested in the instantaneous rate of change at that 1 second. Does that make sense then, folks, on this setup? Awesome. If we're happy with that, then we just go use this function right here. And it's another computation like what we've been doing all along these notes. We're not going for the tangent line in the first two problems. We just want the value of the derivative. It's still a slope, and the slope is always 1 unit divided by another unit. So this time it's going to be something along these lines, meters per second. So plugging it all in, here's how it's going to go. First, we have to take care of that part, f at 1 plus h. It's a degree 2 polynomial this time, so not as nasty as the first one we did on the notes. But let's separate that out as a computation on its own. F at 1 plus h is going to be, plug a 1 plus h in for t up here, so 10 times 1 plus h minus 1.86, 1 plus h squared. Let me try to get that to fit a little bit better. Okay, just under the wire on the border of the page. So that's just this portion right here in orange. Working this out, it's going to turn into 10 plus 10h minus 1.86 multiplying. When we FOIL out a perfect square polynomial like that one, it turns into 1 plus 2h plus h squared. So looks like we want to distribute through and then start collecting our like terms. On the next step, we have 10 plus 10h. Distributing that through, we'll get negative 1.86. And I'm sensing the need of a calculator. Let me grab one real quick. Now 1.86 doubled. That's going to give us a negative 3.72h. Then lastly, minus 1.86 h squared. So still we have like terms. We have 10 minus 1.86. Let's call our calculator back. 10 minus 1.86. That's going to give us an 8.14 for the constant term. We also have 10h minus 3.72. So 10 minus 3.72 gives us 6.28h positive. So let's see, I've combined 10, negative 1.86, 10h, and negative 3.72h. That's the last term that hasn't been accounted. Minus 1.86 h squared. So this right here, we'll go in where we see this orange bracket. One more to go. Let's see, I'm running out of colors. I'll use this pen right here. And let's calculate f of 1 as well. We might as well, if we have it all in the margin, let's just continue with that quantity. F of 1, that's a little bit nicer. That's just plugging a 1 up here. That'll give us a 10 minus 1.86 altogether. And we've done that before. That turns into 8.14. So following the orange bracket, the purple brackets, we'll just substitute those values right back in. And now we're ready to crank out the whole limit. Any questions first, folks, with the algebra on the margin? Okay, nearly there. So let's work this out next. Pretty much just plugging stuff in, but let me make sure I have extra space on the left here. It's equal to the limit as h goes to 0. Pretty decent fraction this time, it looks like. So first substitution orange will be this one, 8.14 plus 6.28h minus 1.86 h squared. Finally, we'll take minus, see the value in the purple bracket, 8.14 when we calculated that. Then mathematical miracle occurs. We can't do this limit with an h in the denominator unless 8.14 cancels, but it does in fact cancel. Tells us we're on the right stage. Now we just want to factor out h in the numerator and do one final cancellation before evaluating the limit. So it's now the limit as h goes to 0. Factor out h, leaves behind 6.28 minus 1.86 h. All of which is divided by h, and this was our critical step. With that h canceled, we can take the limit as h goes to 0 by directly substituting a 0 right in here by that 1.86. All that's left over then is 6.28 meters per second. So if you have an initial velocity of 10 meters per second when you threw the rock upwards on the planet Mars, then after 1 second, it's still moving upwards pretty fast, but due to gravity, the velocity is getting less and less. Eventually, that'll turn into a 0, and then eventually the velocity will be negative, but that just means the rock is now coming down before it hits the surface of the planet. But that's essentially what our derivatives are trying to give us. It's always a rate of change, but it's an instantaneous rate of change. And you can imagine just about anything interesting in physics, sciences, and such is going to be some way tied to this. We're not interested in just ordinary distance, ordinary time. We're interested in distance divided by time. Things like these are very, very interesting once we look at rates more and more. And it's calculus that allows us to get instantaneous rate of changes like we just computed here. So again, if you imagine you're driving a car, that number we just calculated is your instantaneous velocity that you would be looking at a readout. Well, any last questions, folks, with our last problem here on the notes? Well, we got through it, folks. That's the introduction to the derivatives. Section 3.2 is still a bit of an introduction. And then after we get past 3.2, the course starts cooling down a little bit. This is pretty intense work dealing with the definition of the derivative, that thing up there. But there is a lot of shortcuts, a lot of really nice formulas that take this process and start to streamline it a lot. So it starts cooling, the course starts cooling off. We start picking up differentiation rules in section 3.3. But first, we're going to turn to just looking at the derivative one more time. Section 3.2, the derivative as a function. Think of it also, it's kind of a review section in a certain sense, but there is new information there. So let's be careful with what that is. And where did I go here? There it is. The one thing we hinted at the start of class is the moment you define the derivative, it is a function in its own right. And we want to get a handle on how would we plot that function then? We're first going to see how to do it by graphs. Well, that'll be our major thing that we're looking at, doing it by a graph. Then down below, we're going to directly calculate f prime at x. Notice the only difference here is that there's an x variable, not an a. But that's just emphasizing it's a function of x as well. And you could just directly plot that thing after you calculate it. First, we're going to take a look at what should the derivative actually look like if you were to plot it by hand, given a graph like this below. So the way the notes start out are, we have the reminder, here's the definition of the derivative, same limit as we've been taking before as h goes to 0. But if the value of this limit exists, then it's always equal to the slope, massive emphasis on that, of the tangent line at the point x f of x. Below, I have a theorem that we'll come back to, but we might as well look at it now. The theorem is telling us if the derivative is positive on the interval, oh, sorry, I didn't mean to scroll, then f is increasing on that interval. And if f prime is negative on the interval, then f is decreasing. And we can turn that around. So for example, this says a graph of y equals f of x has been provided. We know where the function's decreasing, where the function's increasing. Turning this around, that'll tell us where the derivative is positive and where it's negative. So we'll take our time with this problem because I think it's pretty tricky. We'll graph one of these as just a generic problem, and then we'll do it again where we have an applied setting, like on example 2. So because this is tricky enough, let's write down a sequence of steps, a best practice for trying to get a graph. It says a graph y equals f of x is given below. So here's y equals f of x, just to emphasize. And our goal is to do this. We want to plot the derivative f prime at x down below. So here's our step 1. Find the horizontal tangent lines. The reason that's a critical step is, scrolling up for just a moment, the horizontal tangent lines are important because the derivative of f is the slope of the tangent line. So if the tangent line is horizontal, going like this, that means the slope is 0. The derivative is equal to that slope. So at horizontal tangent lines, f prime of x is 0. And that's always a good start. If you're plotting a function, find where it crosses or just touches the x-axis. That's what step 1 is trying to do. So horizontal tangent line would look like that. And if you look at the graph carefully, you'll find a horizontal tangent line where the curve goes from decreasing through here to increasing. So it's a transition point on this graph. There's one horizontal tangent line. Here's another one where it went from increasing to right at that point, decreasing. And then a third tangent line right there. Once we have those tangent lines, we're ready to start plotting right below. Well, at least 3 points. We have f prime as 0 here, here, and here. Using this idea, the derivative is the slope of those tangent lines. So here's the graph right below. Trying to give about the same scales of the axes. And this is going to be for y equals f prime at x. So all we know for sure is that the derivative f prime at x is going to have value of 0 right here. So go down below. There's 1 point. We have a value 0 right here. So the derivative of f is 0 in that location. We cross right at the origin again. Likewise, your derivative here gives us another crossing point there. So we have 3 points, infinitely many more to go, but this is always a good spot. We're showing where it's going to cross or touch the x-axis. Any questions at all, folks, with getting those 3 points to start?
I have a question real quick.
Yeah.
So obviously the two at 0, the two tangent lines are at 0.
Mhm.
So why didn't we put the dot that's at y is, I don't know, like 3? Why didn't we put that on the same place for the second graph, if that question makes sense?
It does, yeah. What makes this one tricky is I don't have any real scale on the x-axis, but if we imagine that this was a number, say -1,
Mhm.
0, and a +1,
Mm-hmm.
then we had the 3 horizontal tangent lines. So that means f prime of -1 had to be 0 there. And down below, that was meant to be our -1, and there's +1. So right here, horizontal tangent line means take your -1, plug it in. The derivative gives a value of 0, so we plotted 0 right there. Does that make sense so far, visualizing it that way?
Yes.
Awesome. Let's keep on going just to kind of emphasize that process. Over here, we had a horizontal tangent line.
Mm-hmm.
The input was 0, so we can write f prime at 0 comes out at 0. But that means we plotted that point there, 0, 0 for our next coordinate.
Oh, I gotcha. I didn't realize we were using that equation.
Oh, gotcha. Yeah. So yeah, we're using the values here just to plot the points down below. And it's really tricky because it's 2 graphs simultaneously. And this one is a graph of all the slopes, essentially, being the derivative. Well, other questions at the moment? Okay, I might as well just to finish off this list. Here at x is 1, we have a horizontal tangent line. So we can come over here and say f prime at 1 is 0. Then this is telling us at the point where x is 1, the height must be 0 as well. So we got that third point nailed down. So now we need to do the difficult work of finding all the other points, but this is definitely a good start. We're on our way with this. Other questions at the moment? Okay, here is what I would call a good step 2 in this process. Again, this is a really tricky thing. Graphing a derivative based off the graph of the function is something that I always take really, really careful steps on. It's tricky to do just right. So here's the step 2 I would take. For step 2, find the regions where f is increasing and f is decreasing. I wrote INC for increasing and DEC for decreasing. So taking a look at the original function, we're decreasing here up to the tangent line. So this is decreasing, up to where the tangent line was horizontal. So DEC for decreasing. Then going from here through to that point, it's increasing. Likewise, decreasing from 0 to 1. And here to here, we are increasing. So if we know where it's decreasing and increasing, we actually know quite a lot. Recall the derivative over here is always equal to the slope of its tangent line. So over here, when we go to plot this out, let's see where it should be to the left of -1, below or above. Well, we need a tangent line because that's what the derivative is, the slope of it. So if I put a tangent line here, it would look like this, roughly. Not the perfect tangent line, but the slope would be negative for sure. And in fact, there's always a correspondence. If your function's decreasing, the slope of your tangent line has to be negative. And so that tells us f prime of x is less than 0 when x is less than -1. So in that entire region where we said decreasing, the punchline is the derivative is negative, so it's below the x-axis. It comes in like that. Let's pause right there, though. Any questions about that so far? Okay, I feel like we should call this an official third step, so let's do that right here. Once we found where the regions where f was increasing and decreasing, we can now say f prime of x is less than 0 whenever f is decreasing and f prime of x is bigger than 0 whenever f is increasing. So the moment we found the decreasing, increasing regions, we were just saying, where does the curve itself lie above or below the x-axis, the curve for the derivative? So going across -1, we were increasing. Tangent lines are positive here if you visualize it by the red dot, and the derivative is the slope of the tangent line. It has to be positive as well. So it stays positive, but eventually when you get up here, it hits a horizontal tangent line. That's where it goes through 0 on the graph. So we come through like that. When we're in this region, we're decreasing. Tangent lines go like this, they're negative. The derivative is the tangent line, so it's below the x-axis, being negative. So out here, we have negative values, but it gets less and less negative here. The tangent line is horizontal, meaning at this value, the derivative is 0 itself. That's why we have that dot right below to connect through. Finally, out here, this function is just increasing. Tangent lines are positive, and the derivative is those tangent line slopes. So it has to be positive as well. So that's the correspondence. If you find where it's decreasing, your curve is below the x-axis. Increasing is above, decreasing below, and then increasing above. The thing that tied it together was where the horizontal tangent lines occur. They're where we mark out the graph, whether it's above or below the x-axis. But that's a pretty tricky process. It's not as bad in the homework since it's multiple choice, but I would encourage you to try doing it by hand first. That way you'll get some extra practice rather than just seeing what the correct options could be on the multiple choice. Well, any questions at all, folks, on getting through that one? Oh, we got a chat. Awesome. So Jamie says, is this an exam question? You know, that's a good question, but I didn't feel like I had a great plotting question on exam 1, so I didn't want to torture people a whole bunch with it. It might come as a quiz question, but let me make this official by actually putting down a note. Let's say officially, this one won't be an exam question. I felt like we got through enough with that flawed exam 1 question where we had to plot stuff. But just so I don't forget, okay. Yeah, I didn't intend this one to be an exam question. More, I'd say the bigger takeaway on this one, Jamie, is really this idea. It's always going to come back in chapter 3, chapter 4, and beyond to always remind ourselves it's the derivative f of x. We can calculate it this way. We'll find fancy formulas in section 3.3, but we can never lose our way that it's meant to be the slope of the tangent line. And plotting it really emphasizes that. So that's the bigger takeaway on this question. Other questions at the moment? Okay, let's see if we can get through 1 or 2 more problems. So the next one, we have a function that's provided, and we want to calculate the derivative as well. But notice our derivative is written in a really weird way down here. So we should pause and talk a little bit about the notation like we have above.
There you go.
So one thing that's kind of tricky in calculus is there's a lot of notation. It's information dense. The information described there is important. Think, for example, if you're taking maybe limit as x approaches 2 of a function, versus limit as x approaches infinity of a function. On paper, those look like you're asking for the same thing, but in practice, this is totally different. If this limit exists, it means the function had a horizontal asymptote. If this limit exists, that means the function is either continuous at 2, or we could simplify to a continuous function at 2 and get a value out. So limits have their own thing with notation, but so do derivatives. The way we've been indicating them is this way. F prime of x. If we have a function indicated as y equals f of x, occasionally we might just indicate the derivative this way, y prime for a shorthand. And these ways of indicating derivatives are known as Newton's prime notation. For one of the co-founders of calculus, Isaac Newton, he liked this notation because it's just really easy to express. But there was another founder of calculus. This was a long time ago, so they didn't have email or anything like that. They discovered calculus independently of each other. And in Germany, Leibniz used this notation, referred to as Leibniz notation in his honor. And Leibniz notation, the first time you see it, it looks like we're taking something simple, f prime of x, that's the slope, and turning it into something big. It could also be written as dy dx, or for emphasizing the function, df dx. And just a slight change on the notation, we might say the derivative with respect to x of the function f of x. And there's other strange notations. We won't use these two in the book. This is more for completeness. But the purpose of these kind of notations are sometimes whenever you have variables that aren't just y and x, we like using these kinds of things. For example, in the graph down below, we have t for hours, p for yeast cells. We could write the derivative this way, p prime, but that might be ambiguous if there's more variables. Down below, this is saying we're taking the derivative of the function p, population, with respect to one specific variable, t for time. So reading these out again, that's our Leibniz notation. And if you see a dy, or you got my pen tool, there we go. If you see a dy dx, this is read as the derivative of y equals f of x with respect to x. So it's kind of a beast of a notation, but if you're ever doing something that's more in an applied setting, it's more common as a notation. So it's something that we'll train our eyes to get used to as we move through the chapters in chapter 3. So that's our quick discussion on notation. The first 5 are pretty common, but I would say the most common you'll see in this course are going to be the first 4, are the ones that come up more routinely. Any questions at the moment, folks, about the notation? Okay, well, let's make this example 2. Looks like this is going to be a good last problem for the day. Let's give it a new page just so we're not cramming things in. It says here on example 2, this is the graph of the population function p of t for yeast cells in a laboratory culture. And it seems about right. This looks like realistic data. Right here at 0, the population is just above the x-axis. So they started with a small culture, but as time progresses, it starts increasing rapidly around the 5-hour mark. But then when you get it closer to 10 hours, looks like there's maybe lack of space, lack of nutrition in the culture, and the population size starts to even out right around the 15-hour mark. It's always increasing the whole time. That means our derivative, when we go to graph it, part A, our graph is always going to be above the x-axis. But how far above the x-axis? Well, that just depends on how fast it's increasing. Notice it looks like it's approaching a horizontal tangent line right here. So in this location, we should have something close to the x-axis. But let's give this a try going really carefully. First thing we ought to do is just drop an axis right below. Try keeping the scale as the same as best we can. with understanding we're doing this by hand, so it doesn't have to be perfect. My axes are kind of tilted here. There we go. So this is T hours again, but here we're plotting dp dt. Just to emphasize, we're plotting p prime at t, the derivative of the population function. So out here, let me see if I can zoom in just a touch to really see that. So out here, we have a horizontal, well, not quite a horizontal tangent line, but pretty close. If I put a tangent line there, it would look about like that. So it's positive, but not by much. That means the derivative is going to start off by being right around here, above the x-axis. As we move further out, I'd say right around this location, our tangent line is going to be the most positive it could ever be. So let's put down at the 5-hour mark. Our curve is increasing till right about some level right around here. That's where it's increasing the fastest. Then moving off beyond 5 hours, say you're around here, the derivative starting, oh, that's a terrible tangent line. Let me try again. The derivative is still positive, but it's not as positive as it was before. Right around the 10-hour mark, for example, if we plot one at 10 hours, this one's starting to look dang near horizontal. So if we go down to the 10-hour mark, our derivative is always positive, but it's becoming less and less positive because the slope is becoming closer and closer to 0. So it starts to level off around here. Then finally, way out at the 15-hour mark, that pretty much looks like it's a horizontal tangent line to my eye. It's probably still above the x-axis or still slightly positive. I would say out here, it's approximately 0. So at the 15-hour mark, we're somewhere around here. I'll put a dot just above to say, doesn't look like it might be exactly 0, but very, very close. So the rest of the graph would look about like this, if I could get it to connect well. So this is y equals the derivative of the population with respect to time, dp dt. Well, any questions at all, folks, with this drawing here? Okay, let's only our second drawing. We're not going to do a whole lot of them. And like it was clarified earlier, this is not really an exam question. Think of this as just a reminder that dp dt, or if you call it p prime at t, it's always the slope of the tangent lines that we see right up here. So this question is about the slope of the tangent line, but it's also a major notation kind of question. When we have Leibniz notation written this way, dp dt, it can also be expressed when we do a function value in this way. You have dp dt, that's just the derivative p prime. The vertical bar you see here with t equals 5, this is called an evaluation bar. It's saying the derivative with respect to t when t is at 5 hours is 30. So that gives us a unit up here. We had a height of 30. And what we want to do is, well, we know the derivative is 30. We want to provide a practical interpretation of that using the context. That deserves yellow highlighting. This one is a routine exam question here, but it's one we're going to come back to a whole lot because it's really pretty tricky and it's something you have to see repeatedly to get a good feel for it. It's also probably the more important kind of question because what's the value of calculating a derivative if we don't even know what we calculated? So we'll take our time with this one, make it our last problem of the day. Any questions first, folks, before we interpret this derivative? Okay, well, let me take a look at our units again. This is a good graph just to have available when you go to interpret your derivative, just so your units are looking at you when we don't have any misinterpretations. That's way too big. Let me fix that real quick. Okay, now let's give this interpretation of the symbol right by the red dot, the whole expression. Well, first, dp dt is a rate of change. So we can say the rate of change now, again, think about your speedometer. The speed you go, the rate of change you're doing, depends on time. It's one rate at 1 minute, a different rate at another minute, say if a light turns green. So when we say the rate of change, we have to be specific. Let's say at the 5-hour mark of the experiment, so we have to say, because we're doing context, rate of change of what? Well, we can come up here. P is referring to yeast cells. So now we'll say the rate of change. 5 hours into the experiment, they've been growing for 5 hours in the Petri dish, of the yeast cells is, well, it says here 30, but that would be 30. Come over here, cells per, or a division bar, up to you, hour. So the speed at which the population is increasing at the 5-hour mark was the 30 cells per hour, is what this is all saying. If you put in a different value here, say 4 hours, we would get a different value here, so it would just be a different rate. But that's our first look at interpreting a derivative. We'll see it again in section 3.3 and definitely a lot in chapter 4 when we're doing applications of the derivative. But any last questions, folks, on working through this notation and getting that interpretation out? Okay, again, think of this section 3.2 as basically a rehash of section 3.1. We're focusing a little bit more of the geometry of the derivatives. And so when we come back on Wednesday, we'll actually calculate a couple more by just using the geometric nature of the derivative. We can do some really fast problems on part A, part B. Then finally, we'll practice doing this difference quotient again, the definition of the derivative. Only difference in these notes, like we mentioned, is we're calculating f prime of x instead of f prime of a, but we're really doing the same exact thing, whether you're in section 3.1 or 3.2. So that's where we'll end right here for the day. Next section or next class on Wednesday, we'll finish off 3.2 and start working through section 3.3 as well. Any last questions at all, folks, before we call it a day? Okay, well, have a great afternoon, folks. If you have any additional questions, I'll be back on for the office hours right at 3:30. Take care, everyone. Yep, you bet. Have a good one.